Hi, today we're going to look at transformers. Do you see this pic here? This device in this picture over here? Well, probably you've seen this near your homes. Probably you've seen this while going to school. This device, that is out there on the street is what is called a transformer. And this device is very important in bringing power or current to your homes. So today in this session, we're going to look at the working of a transformer, the basic principle that drives a transformer. What is a transformer? Well, as the name suggests, it transforms something. Well, it transforms voltage. It transforms voltage from one value to another. To start with, let's look at the basic principle on which the transformer works. The basic principle that it works on is mutual induction. Now, we have seen this concept before, but I'm going to run this concept again for you so that it is a revision for you. Now, in mutual induction, there are two coils, and these coils lie adjacent to each other. This is coil 1 and this is coil 2. Now, an input voltage is given to coil 1, in this case an alternating current. So this is coil 1. An input voltage is given. Now there is a change in the flux with respect to the primary coil or coil 1. Okay, so as current passes through, or there is a change in the current in coil 1, there is a change in the flux linked with coil 1. Now this flux is also linked with coil 2 as coil 2 lies adjacent to it. Now the change in flux in coil 2 induces or a voltage in coil 2, and this is mutual induction, or the principle of mutual induction. So this is the basis on which transformer works. Now let's look at it in detail. First, let's look at what constitutes the transformer. Okay, so the basic framework constitutes of an iron core, or the soft iron core. So right in the middle of a transformer is a soft iron core. On one end of the soft iron core is a coil, and this coil is called the primary coil. Primary coil. At the other end of the soft iron core is another coil, and this coil is called the secondary coil. Now, the input voltage is given at the primary end, and the output voltage is taken from the secondary end. So the input voltage is VI, and the output voltage is V0 or VO. Okay. Now, something else to note here is the number of turns of the coil of the primary coil. So we are denoting this as NP. It is the number of turns of the primary coil. Similarly, the number of turns at the secondary coil is called NS. Now, typically in a transformer, NS will either be greater than or less than NP, right? Now, the input voltage which is given to a transformer is typically an alternating current. Now, this is so because the value of current keeps changing. As the value of current keeps changing, now two things are going to happen. First, so the current flows into the primary coil, and there is a change in flux, magnetic flux involved in the primary coil. Now, due to this change in flux in the primary coil, an EMF is induced in the primary coil, and this is called EP. So this is given by the expression EP is equal to NP into d phi by dt. Now, this obviously expression comes from electromagnetic induction, where the induced EMF is equal to the number of turns in the coil into the rate of change of magnetic flux. Now you can see that this is caused by self-induction, because the flux is created by the primary coil itself. This constitutes to self-induction, right? So initially an EMF EP is induced in the primary coil, but the changing flux is also linked with the secondary coil, and therefore an EMF is induced in the secondary coil, which is called ES. Okay, and this is due to mutual induction, as we saw the principle. Therefore ES is given by the expression NS d phi by dt. number of turns in the secondary coil into the rate of change of magnetic flux, and this is created by mutual induction. So there are two EMFs being induced here, one in the primary coil and two in the secondary coil. The first one due to self-induction and the second one due to mutual induction. Now I'm going to make an assumption over here to simplify this whole situation. Let us suppose the resistance in both the coils is equal to 0. Okay. In such a case, the input voltage is equal to the voltage induced in the primary coil, because the resistance is 0, and therefore it is equal to Np into d phi by dt. Right? So this is equation number 1. And similarly, the output voltage will be equal to the EMF induced across the secondary coil, which is equal to Ns d phi by dt. This is the second equation. Now, if we divide the second equation by the first equation, we get VO, V output by V input, is equal to Ns by Np, or the ratio of the output voltage to the input voltage is equal to the ratio of the number of turns of secondary coil to the number of turns of primary coil, right? Rearranging this equation, I'm going to write this as V output therefore is equal to Vi into Ns by Np. Now therefore the output voltage is equal to the input voltage into the ratio of Ns by Np. Now when this ratio is greater than 1, that is the number of coils of secondary is number of turns in the secondary coil is greater than the number of turns in the primary coil, the output voltage is going to be greater than input voltage, and this is called a step up transformer. A step up transformer. Similarly, when the input voltage, when the ratio is less than 1, the output voltage is going to be less than the input voltage, and this is called a step down transformer. Right? So we've seen when an input voltage is given, an output voltage is taken out from the secondary side, and this output voltage is either greater than or less than the input voltage, depending on whether the number of turns in the secondary coil is greater than the number of turns in the primary coil or not. Okay, so we've seen voltage over here. Now what happens to the current in the primary coil and secondary coil? So we'll see this on this next slide. Now to understand the current, first we need to understand the input power is equal to the output power. Now this takes from the conservation of energy, that's pretty clear. Power is equal to voltage into current, right? So the input voltage into input current is equal to the output voltage into output current, and or the input, rearranging the input output current by input current is equal to the input voltage by the output voltage, which is equal to Np by Ns. Okay, now if you see this equation, you can see therefore therefore if the output voltage is high, is greater, goes up, the output current comes down, and if the output voltage comes down, then the output current goes up. Hence the power remains constant. So this here is the basic working of a transformer.